much. I'm actually going to try to squeeze in two parts in this presentation. The first part is about this assessment of various direct numerical simulations for boundary layers, and sort of try to establish what criteria one could look at in order to quantify the quality of the simulation. But then also in the second part, also a bit triggered due to the various discussions we had during the workshop, I'd like to show you, maybe for some of you it's show you again some of the flow visualizations that we have obtained in our boundary layer. I'm not trying to answer the question about what kind of coherent structures or hairpins we have, but I just like to contribute to this. So this will then be in the second. But let me now first start with the first part, namely this an assessment of the quality of direct numerical simulations. So our starting point is essentially, I stole this slide from Gary. Essentially, when we look at DNS data, the good thing with DNS data is we always get straight lines. So there's no sort of measurement error involved. There's no scattering for one particular simulation. It's just always one straight line. So we are maybe to some extent a little bit fooled with the accuracy that is actually underlying the whole machinery of the forming units. So that also means that we have a great deal of trust in simulation results. And to a large part, this is also justified. For example, here when we look at the gradient of the velocity profile for various small-bounded flows, we see perfect agreement up to maybe a set plus of y plus of 60, or if we are great, we can also say we have perfect agreement up to a position of 200. So it is really, we can reach very, very good agreement with various simulations. So this is the starting thing. If, on the other hand, if we go to experiments, so this I can say as somebody that does simulations, usually the picture is not as nice. You have a great deal of scatter around maybe a mean value or some correlation. So if we are used to look at experimental pictures, then this is the situation that we are faced with. This is just one example for a shape factor in the turbulent boundary layer by William Fahrenholtz about 10-15 years ago. Now, in recent years, we have been able to also reach a large part of this plot via numerical simulations. So what we can do now with the simulation more or less covers at least range here maybe. Of course, it's a bit deceiving. This is a logarithmic plot, so probably will not get much further here. But still, we can reach already quite some part of this. Now, what we did recently is we just collected all the DNS data that pertains to the turbulent boundary layers. And we plotted it here, just a shape factor as a function of rho theta. And unfortunately, now the picture that we had before, where we had this the gradient of the velocity profile, everything was perfectly on top of each other. Unfortunately, this picture doesn't seem to hold any longer. So also, when we go to more and more complex flows in the numerical simulations, we also get into the situation that we suddenly get a scatter of data points. And even in very, very basic quantities, such as a shape factor, something in integral quantity. So, and now of course, what we need to understand, or what we need to learn maybe to some extent, is also to really scrutinize DNS data, to really go into the data to try to understand, okay, are all the conditions, for example, for a fully developed flow fulfilled? Is this data point trustworthy, and if so, to what accuracy? So, in a way, what we were trying to advocate is to use similar methods that people use in experiments to judge whether the quality of data is good also in simulations. Now, let's get a bit more specific. The databases, DNS databases that we have been using to sort of put together all these data points are listed here. So we start with the work by Scholart 22 years ago. It includes the work by Schoolbigger at KTH. We have a series of simulations by Kuhn Hudson and Overlock. We have the simulation by Ferrando and Kobashi. Also the recent simulation by Jimenez and co-workers. We have, of course, also included our own simulations and also the simulation Now, I don't want to focus in this talk about sort of blaming people for not having good results or say somebody else has good results. So I have here the key for the various symbols, but this is the last time you see that. So I will not tell you who it is. Now, if one goes into the data and just looks, what is the major difference between the simulations? There are essentially two things. Maybe one thing I should say before. All these simulations were performed with good numerical methods. They're all fully resolved, whatever fully resolved means, but still they're not under-resolved DNS. They're all well-resolved DNS. So this cannot be the reason for discrepancies that we see. So the main difference is that these simulations are essentially two things. One is the domain size. Since we're talking about spatially developing flows, the streamline direction is not homogeneous, so you need to have some sort of inflow-outflow treatment. So the size of the domain is one point, but the other point is how turbulence is actually introduced. Whether one uses a recycling method or whether one uses a turbulent method. Just to give you an idea, you have to consider this more as a sketch than as a sort of fully detailed picture. I just tried to sort of put into this picture all the various boxes of these different relations. So you see that there are certain boxes that start fairly downstream and are maybe comparably smaller, and we have other simulations which are very wide and very long. And as we will see later, probably this length and width is the crucial point in getting good agreement with the explanations. Also in the next plots, what I include in some plots are some data coming from channel flow simulations. Channel flow, or the good thing with channel flow is that it is homogeneous in X, so one is not faced with the problem of needing to generate turbulence in different ways. So all the blue triangles are channel flow results. Now, when we started to compare the data, the first thing we observed was essentially is shown here in this plot down here. We just took everything, all the data which we had at rate theta of around 700, and we plotted. You can see here a blow up of the region here in the free stream. Now, of course, the immediate question was, okay, if you, for example, have a profile that looks like this, what is U infinity? Of course, we could just take U infinity as being this value, but is this the correct U infinity? Or should one average here, or maybe take that point? Similar questions here. What is the correct U infinity to take? And of course, if one asks somebody that does experiments, then these people are daily faced with such questions. When you read the numerical simulations, you don't really have this.
Our profiles looks better.
Anyway, so the first thing we needed to do was to find a consistent way of how to actually define very basic things like boundary layer thickness or free stream values. So this was the reason why we actually re-evaluated all these integral quantities for these various profiles. We did this by taking a profile. In our case, we took the one by Tim Nichols, and essentially we fitted it to all these profiles, and then got the integral values like delta 99 or great tau, delta 99 plus, and the freeze stream value directly from the fitting profile. Then also, when we will later see, we'll also evaluate, for example, the Y position, the peak in the streamline velocity fluctuation. Also there, of course, we fitted in a parabola, actually it's a four-order polynomial, and we took the maximum effect, we didn't just go into the maximum data. Just to give you an idea of what this actually means in terms of or how data points move around by doing this re-evaluation. Here on the left side, you see the shape factor now evaluated exactly as the data stands, maybe even using the data points or the values that were given in the respective literature. And here on the right side, you see the re-evaluated values for these points. And you can see that, for example, let's take this behavior of the shape factor. Without re-evaluating it, it's essentially constant, but if you then use this consistent fit with the profile, then you see that suddenly these data points are not as bad as they were looking at this. But I mean, the main point here is that that there is really a difference when you go from here to here. So this might be one important point to actually do when comparing such.
Well, Philip, what's the spread over that curve, the plus or minus?
I think it's plus minus 1.
1%.
I think so, yes.
Okay.
Yes, yeah. It's the same spread here and here.
Okay.
That was the 1%. Actually, this brings me directly to this slide. Now we only look at the re-evaluated values, so we forget about the ones that were not done with the profile thing. So everything from now on is re-evaluated. Then, of course, we also had to come up with consistent definitions of the shape factor. For now, we choose actually the integration here from 0 to delta 99, which of course is an arbitrary choice. But if we do it consistently for all the profiles, then there is still some value in comparing it. But it's arbitrary. Now, if we just look at here how well these various DNSs agree with each other, then we see actually, well, in the end, it's actually fairly good. I mean, everything more or less lies within this 1–2% for the shape factor, for the skin friction coefficient here. It's actually very good. But you need to do this step of re-evaluating. Some other results here, for example, we plot rate theta versus rate tau or delta 99 plus. So here we see everything actually looks very nice. Now, if we go a little bit to more, let's say, exotic quantities, then there starts to be still some spread in the data. So what we look at here is fluctuating low shear stress. So this value that Henrik fixed a few years ago to be 0.4, which is still reasonably correct, I would say. So there is some spread here. So there are some data points which lie a little bit higher. Presumably there is also some transitional effects involved here. There are other data points which are slightly higher. But still, one can see that the data points for the bulk of the simulations somehow converges to a sort of slowly increasing.
The channel flow data are more reliable, they tend to be lower.
Yes, these are the blue ones are the channel flow data.
They're lower.
Yeah, they're slightly lower than this. But still the channel trend is also reasonably consistent with that.
What's the slope of the red line you have just for curiosity?
I have to look it up. Yes. Now we can of course look at all the other quantities that are contained in the data. We can look at the peak in the streamwise velocity fluctuation. Also here there is a spread, but also there seems to be somehow a line here which emerges from all this data, which is astonishingly consistent with what the channel flow is also. a little bit less agreement when you look at the position of the actual maximum. Particularly, it's interesting that here this divergence between low Reynolds number boundary layers and channels. But of course, there is again the question: to what extent are we talking about fully low occurrence in the boundary layer case? Or is this the transition? We can do the same thing for the Reynolds shear stress. Of course, here one important thing to notice is what also Hassan was mentioning last week, that for boundary layers we are generally at a higher level, or we reach or go towards one at lower Reynolds numbers compared to these general flows.
Can I take you back to the one that Fazli asked you, because this is the explanation for the fact that the slopes are different. Yeah, this one here. I don't think the slopes are really different. I think that the channel is taking longer to reach.
That could also be.
Okay. And the explanation was the other slide. I waited for you to get to that.
Okay. So the important thing, what I want to show with all this data is less sort of interpretation or explanation of the data, but rather that if one starts to reevaluate data, then there is, at least for most of the simulations, a nice consensus of how things work for a quite substantial range of Now, of course, these were all sort of integral quantities. We can also start to look at profiles. So here we have, we can focus on the outer part, for example. This is ray theta 2000 and ray theta 2900. All these data points are essentially at the same Reynolds number, but you can see that there is difference. There are two simulations here which are actually fairly close to each other. So probably this seems to be the value that is probably correct, the correct term. Also here at the higher Reynolds number again there is some discrepancy. Again, at the same Reynolds number, and it's not under-resolved or the numerics being And then maybe the last one, showing you discrepancies in terms of the mean profile. Here we focus on the inner part of the boundary layer, and we look at the deviation of the measured mean profile to a master profile. And we can see that also here we reach is very, very close to the plus units, maybe 10 to 100. There is really a spread of different simulations. However, again, here there seems to be some sort of general shape which presumably is the correct one which one would expect. So now the main conclusion of this part is so we have taken all the simulations that are available in the literature, all of them having had good resolution, so the resolution is not the problem for finding discrepancies. The two important points that I would like to make with this presentation is, first one, it is important to critically look at data and, if necessary, find consistent definitions of basic quantities as a shape factor or boundary layer thickness, very much in the same way as one does that in the experiments. And then the second point here is, in the first step, one really has to consider a DNS of these large cases as being an experiment, a numerical experiment, but in the end it's an experiment. So one has to carefully go into the data and assess what kind of quality one can expect from a given simulation. This is really the same thing as one does with experiments. And now, of course, you can say that this is a trivial conclusion, but I think we are fooled a little bit by having all these straight lines in DNS. So this is smooth lines in DNS. And these smooth lines do not really show any error margin. And I think this is something that we need to really focus on in the future. Now, I don't know how it looks for you.
I think you have 4 minutes.
4 minutes. Okay.
We discussion.
Okay. So then I would like to use these 4 minutes just to give you some pictures of the boundary layer simulations that we have actually performed here, which right now covers the domain or the extent from ray theta of 180 to 4,300. It all in one long domain. The choice of having one long domain is, of course, exactly motivated by some of the conclusions that I was mentioning before. So I can skip that. If we just look at the flow in our computational domain, we can see that we actually start here with a laminar flow, we trip the flow to turbulence, and then we wait for a certain downstream distance until we have reached something that we would hope that it's a fully developed turbulence. And then, as the Reynolds number increases, of course also the scales in the flow start to get larger and larger. And you can already see it here that we have also in our simulations large-scale structures that we have heard many times today. But since the time is short, I just want to show you one video that we actually finished yesterday or today. It is a very, very preliminary video. And it just shows the initial part of the domain. We are standing here and we're looking here at the laminar lossless profile and sort of see how we create turbulence. Yeah, so I just played it now.
How far can we see in RE theta or something?
I think up to about this position here is about 1,000. And this position here is 100, 200, 180, 200. And now, due to the nature of how we set up the simulation, we actually undergo transition. We have here a tripwire, invisible tripwire, which creates then streaks, and these streaks break down, and they essentially break down as Neil was explaining before. You get very, very nice hairpin vortices. If we would plot here also the streaks, these hairpin vortices would ride on top of the Radosman streaks. Now I don't know how well you can see it. Of course, these hairpin vortices that are created here, they survive for a certain distance downstream until I think they are sort of disappearing in the flight.
Excuse me, what's the threshold you use to identify these?
Sorry?
What's the threshold in vorticity or something like that?
What we see here is these are negative or isocontours of negative lambda 2 colored with the wall distance. The exact threshold I wouldn't know now, but it's a visual thing. I just chose it in such a way that we can see here these nice arches. Now, the last picture I want to just show you. I was very optimistic here with so many slides, but okay. So the last picture is coming here, where we focus on the region at the theta 4,000. Essentially, we visualize the same thing as we had before, just isocontours of negative lambda 2 colored with the height. So very close to the wall, and maybe you can see it here. There are probably some small streamless vortices which correspond to the whole near wall dynamics. And then what you see here, that's essentially outer layer dynamics. But it's essentially very, very chaotic. And to single out here individual structures appears to be very good. So I think this is
okay. Thank you. Very fast comments.
Very quick question. Could you go back to the slide that was just before your conclusions one?
yes.
I think it was right before it.
Conclusion.
Yeah. No. Yeah. How do you explain this graph in light of what Gary Coleman showed us yesterday, where he basically in the same region showed all of these DNSs were on top of each other in the data.
Because they are not the same DNSs. What he compared was the ICON layer, channels, type, and some boundary layers. And the first three of them, ICON, channel, and type, they all are parallel flows. And there you don't have the problem of tripping or of having long domain. Well, you still need to have long domains, but not for the same reason as in such cases. So I believe that one of the most difficult part of boundary layers is really the spatial development, and that we need to introduce turbulence in some way, and we need to wait long enough until you actually have a profile that was settled down enough to make a good statement.
Okay, thank you. Unfortunately, I guess there is not much time.